Okay, today let's have a look at the first lesson of chapter 4. Today we're going to have a look at the applications of exponential and logarithmic functions and their derivatives. So remember last time we have learned how to differentiate an exponential or a logarithmic function, right? So today let's have a look at their applications. So specifically speaking, the learning goal for today is to solve real-world problems involving exponential and logarithmic functions and their derivatives. So I'll give you some example questions to illustrate the concept. So let's consider the first example. A biologist is studying the increase in the population of a particular insect in the provincial park. The population triples every week. Assume the population continues to increase at this rate. Initially, there are 100 insects. Determine the number of insects present after 4 weeks. And how fast is the number of insects increasing when they are initially discovered and at the end of 4 weeks? Okay, I'll give you some time to have a look at these questions. First, consider the number of insects present after 4 weeks. Okay, let's have a look at the solution together. Okay, first question, write an equation that gives the number of insects n as a function of time t in weeks. So we can write nt equals 100 times 3 raised to the power of t, right? T stands for the number of weeks. And to find the number of insects present after 4 weeks, you can substitute t equals 4 into that equation. So n4 equals 100 times 3 raised to the power of 4. That gives us 100 times 81, right? So there are 8100 insects after 4 weeks. Any questions? Any questions? No? Okay, then question B, to find how fast the insects are increasing at any time. So this is an instantaneous rate of change of the original function, right? So we can differentiate the original function, nt. So note that nt is actually 100 times the exponential function, right? So the derivative of this function, the n prime t, or nt prime, equals 100 times line 3 times 3 raised to the power of t, right? That's the first derivative of nt. And to find how fast the insects are increasing initially, we need to evaluate the first derivative at t equals 0, right? So when t equals 0, n prime 0 equals 100 times line 3 times 3 to the power of 0. So that gives us about 100 times 1.1 raised to the power of 1.1 times 1, right? So that is around 110. So the number of insects is increasing at a rate of approximately 110 per week at the beginning of the first week. Then to find how fast the insects population is growing at the end of 4 weeks, we need to evaluate n prime at t equals 4, right? So substitute t equals 4 into the first derivative of nt. That gives us n prime at 4 equals 100 times line 3 times 3 to the power of 4. That equals 100 times line 3 times 81, which is about 8899. Therefore, we can make the conclusion at the end of 4 weeks, the insects are increasing in a number at a rate of approximately 8899 per week. You have any questions? Any questions? No? Okay. Then let's consider a second example here. A person named Laura has just bought a new motorcycle for $10,000. The value of this motorcycle depreciates over time. Depreciates means decreases, right? The value can be modeled by function. Vt equals 10,000 times e to the power of negative t over 4. Where a is the value of the motorcycle after t years. So there are 3 questions. A, at what rate is the value of the motorcycle depreciating the instant Laura drives it off the dealer's lot? Second, Laura decides that she will stop insurance coverage for collision once the motorcycle has depreciated to 1/4 of its initial value. When should Laura stop her collision coverage? In other words, 1 is the price of the motorcycle. It's just 1/4 of its initial value, right? Question C, at what rate is the motorcycle depreciating at the time determined in part B? Okay, again, I'll give you 5 minutes to think about this question here, okay? Okay. Let's have a look at the solution together. First, question 8. To find the rate of change of the value of Laura's motorcycle, we can differentiate the value function, right? The value function is Vt is 10,000 times e to the power of negative t over 4. So the derivative of this function equals negative 2500 e to the power of negative t over 4, right? You should be able to differentiate this function, right? So this function is a natural exponential function. And to determine the depreciation rate when Laura first drives her back off the lot, we can substitute t equals 0 in the derivative, right? So when t equals 0, we have the derivative of v at t equals 0 equals negative 2500. Therefore, when Laura drives off the dealer's lot, her motorcycle is depreciating at rate of 2,500 per year. Any questions? Any questions? No? Okay, then let's consider question B. To determine when Laura should stop collision coverage on her insurance plan, find the time when the value of her motorcycle reaches 1/4 of his initial value, 2,500. So we can let 2,500 equals Vt, right? Which means 2,500 equals 10,000 times e to the power of negative t over 4. So we need to solve for t, right? To simplify this equation gives us 0.5 equals e to the power of negative t over 4, which means we can find the natural logarithm of both sides, right? So line 0.25 equals line e to the negative t over 4. That means we can solve t is approximately 5.5. Therefore, we know Laura should stop her collision coverage after approximately 5.5 years. Any questions? 5.5 years. Okay, then let's consider the next question. We need to find the rate of depreciation at that time, right? That means actually we want to find the first derivative of v with respect to t at t equals 5.5, right? Okay, so we can substitute t equals 5.5 to the to the derivative function. So v prime at t equals 5.5 is approximately negative 632. Therefore, we know after 5.5 years, Laura's motorcycle is depreciating at a rate of approximately 632 per year, $632 per year, right? Any questions? Any questions? No? Okay, then let's have a look at another example. Okay, so this example question here. A radioactive isotope of gold, AU198, is used in diagnosis and treatment of liver disease. Suppose that a 6.0 milligram sample of AU198 is injected into a liver, and that this sample decays to 4.6 milligrams after 1 day. Assume the amount of AU198 remaining after T days is given by this function. Nt equals N0 times e to the power of negative lambda t. So there are four questions. A, determine the disintegration constant lambda for AU198. Question B, determine the half-life of AU198. That means the time taken for this isotope of gold to reach 50% of its initial value, right? Write the equation that gives the amount of AU198 remaining as a function of time in terms of its half-life. Then last question is, how fast is the sample decaying after 3 days? So in other words, what is the instantaneous rate of decaying after 3 days? Okay, I'll give you 5 minutes to have a look at this question by yourself. Okay, then let's have a look at the solution together. Okay, first question, the amount of AU198 remaining decays exponentially over time according to the formula NT equals N0 e to the power of negative lambda t, right? Where t is the time in days. So at t equals 1, the sample has decayed from its initial amount. N0 equals 6 to N1 equals 4.6, right? We can substitute these values into the equation and solve for lambda. So we have this equation, 4.6 equals 6.0 times e to the lambda, e to the negative lambda times 1, right? Therefore, to solving this equation will give us lambda is approximately 0.266 days. So the disintegration constant lambda is approximately 0.27. The equation for the amount of AU198 remaining as a function of time can be written as NT equals 6 times e to the power of negative 0.27 t, where t is a time in days. You have any questions? This is how we can solve the coefficient lambda, which is called the disintegration constant. Any questions? No? Okay, then let's have a look at question B. To determine the half-life of AU198, determine the time required for the 6 milligram sample to decay to half of this amount. So we can set NT equals 3 and solve for T, right? Okay, so we have the following equation. Left side is 3. Right side is 6 times e to the power of negative 0.7 t. And there is only one unknown quantity t, right? Which can be solved to approximately 2.6. The unit is days. So the half-life of AU198 is approximately 2.6 days. Okay, question C, the equations that give the amount of AU198 as a function of time in terms of its half-life is NT equals 6 times 1/2 raised to the power of t over 2.6, where t is measured in days. Do you have any questions? No? Okay, then let's consider the last one. Find the rate of decay after 3 days. We can first differentiate the function, modeling the amount of AU198 remaining, and evaluate the function at t equals 3, right? First of all, the derivative of NT equals negative 0.27 times 6 times e to the power of negative 0.27 t. Then substitute t equals 3 into that derivative. That gives us n prime at t equals 3 is approximately negative 0.72, right? So this means after 3 days, the sample of AU198 is decaying at instantaneous rate of approximately 0.72 milligrams per day. Any questions? Okay, if you have no questions, let's consider another example. Okay, remember last time we have talked about the pendulum, right? A pendulum is an example of harmonic oscillator, a moving object whose motion repeats over regular time intervals when the amplitude of a harmonic oscillator diminishes over time due to friction. the motion is called damped harmonic motion. So today, let's have a look at damped harmonic motion. The vertical displacement of a sport vehicle's body after running over a bump is modeled by the function ht equals e raised to the power of negative 0.5 t times sine t, where h is a vertical displacement in meters at time t in seconds. The graph of this function is sinusoidal with diminishing amplitude, as shown to the right. Determine when the maximum displacement of the sport vehicle's body occurs, round to the nearest tenth of a second. And what is maximum displacement? Round to the nearest hundredth of a meter. Okay, I'll give you 5 minutes to think about this question here. All right, let's have a look at the solution. First, let's briefly analyze the graph of this function. So note that the graph of this function has a combined effect of an exponential function and a sine function, right? So if we don't consider the first function here, if we only plot sine t, that function will look like this. Right? Okay. So it's probably like this with a constant amplitude, right? So if you add a first function e to the power of negative 0.5 t, as t increases, we know negative 0.5 t decreases, right? And e to the power of negative 0.5 t should also decrease, right? So as t increases, the amplitude of this sinusoidal function decreases. Therefore, it has a overall shape like this, right? As you can see here. Well, the overall shape is still a sinusoidal function, but with a decreasing amplitude, right? Therefore, the maximum displacement will occur somewhere here, right? In other words, you should find the first time the first derivative of this function equals 0. That's the point h reaches its maximum, right? Okay, so following this logic, let's have a look at the solution of this question. So to determine when the maximum vertical displacement occurs, we can differentiate the function and set the derivative equal to 0. Okay, ht equals e to the power of negative 0.5 t times sine t, right? This is a product of two functions. Then the derivative of this function equals e to the power of negative 0.5 t times cosine t plus negative 0.5 e to the power of negative 0.5 t times sine t, right? And simplify that to e to the power of negative 0.5 t times the difference between cosine t minus 0.5 sine t, right? Also note that e to the power of negative 0.5 t is always greater than 0. So if we set the first derivative equals 0 and solve for t, the solution should be cosine t equals 0.5 sine t, right? In other words, tangent t equals 2, right? And first of all, we can find one possible solution. One possible solution is t equals 1.1. Well, actually, if you don't consider any constraints, there should be unlimited number of solutions, right? However, we only care about the first value of t that makes this first derivative be 0. So the first possible value, smallest positive value of t is 1.1, right? Of course, there are some other values that can make the first derivative be 0, such as here, here, or somewhere here, right? But we only care about the first smallest possible positive value of t that can make the first derivative be 0. That's the maximum vertical displacement can occur. So due to the periodic nature of the tangent function, there are unlimited number of solutions. So we only care about the first one. So from the graph of ht, it is clear that when t equals 1.1 seconds, this is the time when the vertical displacement is a maximum. The maximum displacement occurs approximately 1.1 seconds after hitting the bump. Okay, have a look at this solution. Do you have any questions? Any questions? No? Okay, then that's the end of today's class. So remember to complete the homework on Google Classroom and submit them on time, okay?